This is number 5 from the 2019 BC Free Response Set. Non-calculator question here. A bunch of questions like this have been popping up in the last handful of years on the BC test, and they give us a statement about this function here, and k is within the denominator of that function, and that is an unspecified constant. So part A asks us to find the value of k that has to be positive, such that the slope of the line tangent to the graph of this function at 0 equals 6. So hopefully you read part A and you realize right away, all right, I know that f prime of 0 has to equal 6 in order for the slope of my tangent line to be 6. I just need to figure out what value of k makes my derivative equal 6 when I evaluate it at 0. So if you're going to do that, you need the derivative. So I re-expressed k as a negative exponent as opposed to a rational function. And then I used a chain rule for the derivative. So after I did my chain rule, I knew I wanted to put 0 in here and do some algebra with it. So I tried to clean it up a little bit. So the negative exponent term went back to the denominator, changed the sign back to a positive. I still have this present within the numerator in addition to that factor of -1. This is a pretty convenient form of the derivative to utilize for the following steps. So we need to set f prime of 0 equal to 6. So we toss 0 in place of the x's, and that simplifies down to just 2 over k squared. When we set that equal to 6, you can multiply by the k squared to get it out of the denominator. Solving it gets you this, but we were told that k had to be positive, therefore we end up with just the square root of 1/3 as the value of k. That's going to make that derivative have a value of 6 at 0. Part B says, all right, new value of k, -8 now. Find the value of the definite integral from 0 to 1 for this new version of f of x. So what I thought right away was, I need to be concerned about f of x being undefined at 0, at 1, or at somewhere in between. So I factored my denominator right away and just tried to figure out when my denominator was going to equal 0. And it equals 0 at 4, and it equals 0 at -2. None of those values are at or between these limits, so we're not dealing with an improper integral situation here. Also, factoring that denominator was kind of convenient because it kind of implied to me that we're going to have to go about finding this antiderivative with a partial fraction decomposition. So I assumed that I could re-express this fraction as a over the initial factor plus b over the second factor. I then found a common denominator between these two fractions, so I multiplied this fraction by x plus 2 over x plus 2, multiplied this fraction by x minus 4 over x minus 4. So a effectively got multiplied by this denominator, b got multiplied by the other denominator, and then I had a common denominator and the ability to write that as a single fraction. If I multiply both sides of this equation by the denominator goes away, so I don't have to worry about the denominator at all. My numerator has to equal 1 though. So I simplified my numerator a little bit, distributed in my a, distributed in my b, ended up with this equation. Now this equation is kind of goofy. The first handful of times you see something like this, you're probably like, well, how the heck am I supposed to find a, b, and x? I've got one equation to do this. And so the idea you're going to use is called equating coefficients. So the coefficient of x over here is 0, right? There is no x. So the coefficients of x over here, the a plus the b, they've got to combine to give you 0. So you know that a plus b has to equal 0. And the constant terms over here, 2a minus 4b, they have to equal the constant term on the left, which is 1. So if you have this equation and this equation that involve a and b, you can solve that system to figure out what your values of a and b are, and x is totally taken out of the mix. So I solved by substitution, right? Solved this for b, popped that in over here, did my work to isolate a. Once I had a, put it over here, got my answer for b, carried it up to the top of the next column. So a was 1/6, so I just factored that out in front of the integral, and I had 1 over x minus 4 inside the integral from 0 to 1 as the first portion of my integral of f of x. I did break it up into two separate integrals. Right, when I have these two separate fractions, my personal preference is just do it as two separate integrals and put the results back together at the end. So I factored the -1/6 out of that numerator, so rather than adding the fractions together, you obviously see subtraction between my integrals as indicated by the sign of b. Technically, you need to do little substitutions here, but your derivative of x your derivative of u with respect to x for either of these fractions is 1. Nothing has to cancel out, so you're going to end up with natural log of the absolute value of this denominator for the first antiderivative, natural log absolute value of the second denominator for the second antiderivative. Evaluate those at 1, at 0, take a difference, and you have your result. Could have left my result like this, right? No need to simplify on a non-calculator AP grading scenario, but I chose to do that a little bit. And you can use some property of logarithms here to even take that a little further and make it a little bit nicer. But full credit for what I have here, and then full credit for what I have here after distributing that negative and canceling the 1/6 natural log of 3 terms that were opposites. And the next part of this says, all right, now k is equal to 1. Find the value of this definite integral or show that it diverges. So it's kind of nice of them to tell us that the integral might diverge. So they've kind of implied with the wording that this is an improper integral. But if you put 1 in place of k and factor your denominator, you end up figuring out that f of x is able to be re-expressed like this. And that function is definitely undefined at 1. 1 is smack dab between the limits of integration. So when you deal with an improper integral where you're undefined at a value between the limits of integration, you're going to need to go ahead and break your integral up into 2 separate integrals added together. So we're going to do the integral from 0 to 1 and then add the integral from 1 the rest of the way to 2. Now, in order to carry out an improper integral, you basically need to trick the fundamental theorem of calculus into working. This integral right here is undefined. This integrand, is undefined at 1. The fundamental theorem of calculus says you're able to apply it to find the value of your definite integral if your integrand is continuous at and between the limits of integration. So we trick the fundamental theorem of calculus into working for us by replacing that limit that we have an issue with a dummy variable. We then turn around and let that dummy variable approach 1, but in this case it's only from the smaller side with what I'm referencing right now, because within this interval we're only ever going to be on the smaller side of 1. I do a similar setup over here with the right hand portion. Lower limits the issue. I'm only going to be on the bigger side of 1 as I'm within this interval. I did use FTC part 1, right? I found my antiderivative. I carried out a little u substitution up here. Be careful you don't get natural log of u squared or anything like that here. Power rule applies, so that'd be a common mistake that I would worry about people making because you have that happen so frequently when you do antiderivatives, but power rule applies, right? Add 1 to that power, divide by the new power. Cleaned it up a little bit. Here's the antiderivative, so I had to bring that down here. Toss in the limits of integration. So I tossed in r initially, I tossed in 0, took a difference. Similarly, I tossed in 2, I tossed in r, took a difference. And then I had these limits as r approached 1 to try to reason out. So when I put 1 from the smaller side right here, a number like 0.9, I subtract 1 from that value. I get close to 0, but I come out on the underside of 0. And negative 1 divided by a negative is definitely a positive, and 1 divided by 1/1,000,000th, if I multiply by the reciprocal, is 1/1,000,000th. No matter what happens over here, if a portion of the integral diverges, and this being infinity minus 1 or just infinity indicates that it does diverge, that's going to imply that the overall integral is going to diverge.